first let's determine the kinetic energy and the potential energy of the system. First, let's identify the kinetic energy of the system. Okay, so in the problem, the problem said that this object is pressed as far as x. So it means the position of the object is x. And then the problem also said that the stiffness of the spring is k. Okay, so from this problem we can derive the x, or the position, as the speed. Okay, so we derive the x over the time. We write it as phi is equal to dx over dt. It equals to x dot. It means the speed of the object. And then from here we can get the kinetic energy of the system is equal to a half of mass times the speed squared. Okay, this is the kinetic energy of the system. And then we will try to find the potential energy of the system. Okay, so in this problem there is just only spring available here. So the only potential energy of the system is only the potential energy of the spring in the system. Okay, so the potential energy is half times the stiffness of spring, k, times the position of the object squared. Okay, so this is the potential energy. And then we label the kinetic energy as T is equal to, just that again, and then the phi, or the potential energy, is equal to a half times k times x squared. Okay, so we have already identified the potential energy and the kinetic energy of the system. So after this, let's put the T and phi into the Lagrangian equation of motion. The definition of the Lagrangian equations of motion is the equation is equal to T minus phi. Okay, let's substitute the T as a half times n times x dot squared. And then let's substitute the phi as a half times k times x squared, or the position of the object squared. Okay, so this is the equation of motion of the system according to the Lagrangian mechanics. So now let's put this equation into the into the Euler Lagrangian equations of motions. The equations is the derivative of partial derivatives of the Lagrangian equation of motions over the x dot over the time minus the partial derivatives of the Lagrangian equation over the position of this system or the object, and that's all is equal to 0. This is the equation, the Euler Lagrangian equation of motion. So let's find the what's variables that contains x dot. So we will derive it. We will do a partial derivative to the variables, and then let's find the variables that contain the variable x2, so we can do a partial derivative to the equations too. Okay, so first let's derive the Lagrangian equation over the x. Okay, and then we will get the partial derivatives of the Lagrangian equation over the x is equal to kx. Let's assume this as the first equation, and then we will make a partial derivative of the Lagrangian equations over the x dot, and then we will get it's equal to mx dot. This is the second equation, and then we will derive this equation again over the time. So this is the total derivation, but this is the partial derivation. Okay, let's derive this equation over the time, and we will get the result is equal to m times x double dot. Okay, so this is the third equation. So let's substitute the first and third equation into the Lagrangian equation of motions. I mean Euler-Lagrangian equations of motion back. Okay, so we can find that the derivative of partial derivative of the L over the x dot over the time is equal to mx double dot minus I forget the minus sign. I'm sorry. In the first equation there must be a minus sign, because in here we can see it's minus a half times k times x squared. Okay, so we back to the Euler-Lagrangian equation of motion. The Euler-Lagrangian equations of motion is become mx double dot minus negative kx is equal to 0. Minus times minus is equal to a positive value. So we will get mx double dot plus kx is equal to 0. And then let's divide both sides with m. Okay, and we will get x double dot plus k per over m times x is equal to 0. Okay, so from here we can get the solution of the problems, but first let's identify what kind of equation is this. And then if we study about the oscillations of a system, this equations is the kind of oscillations equations. It's very identical with equations of the double derivative of x. The double derivative of x over the time squared over the time over the double time plus the position, the omega or the angular velocity squared times x is equal to 0. This is the general equations of oscillations. This is the acceleration of the system, and then this is the period of the system. Okay, so we can assume that the k per over m as the omega squared. So it means we will get in this equation omega squared is equal to k over m, and then it means omega is equal to the square of k per m. We will change the value of omega because omega is equal to 2p over the period or the capital T, and then we will replace it into here, and then we will get 2p over T is equal to squared k per m. So from this we can get the solution of the problem. So we will get the period of oscillations of the system is equal to 2p times squared of m over k. So this is the solutions of the problem. Okay, so that's the steps on how to solve a physics problem using the Lagrangian equation. And on these topics I teach the method, the way of how to using this method using is to solve the problems about the oscillations of a system. Okay, so that's all for me. Thank you for your attention, my teachers, and good morning.